the speaker. Hayashi-san、聞こえてますか？私の声。
OK、OK。はい、聞こえてます。はい。OK。
で、カメラオンにしたんだけど。スリップにならないよね、これは。急に。多分。なんか画面はだんだん暗くなってきてるんだけど。じゃあそれでいい。はい。わかりました。
じゃあ始めましょうか。はい。I'm Ryuhei Mori from Nagoya University. This morning there are 3 talks. The first talk will be given by Francisco Buscemi from Nagoya University. So please.
Okay, thank you very much to the organizers for having organized this event, and to the people here in the room and the people that are looking at this presentation online. Okay, so today I would like to present something that we've been doing with my students, Shintaro Minagawa and Kodai Kobayashi, and some collaborators abroad about quantum measurement theory. Okay, so these are the 2 references. One paper, the first one was published in 2020 with Eric Chitambar and a PhD student of mine at that time, Wenbin Zhou. Then there is another one which has been published very recently on quantum, about the incompatibility of quantum instruments, and then the last one which is still under review, and this is one about sharpness. So let me just review the main concepts that I will be using in this talk. So first of all, I will only consider the finite case, finite discrete case. So all sets are finite and spaces are finite dimensional. So what is a POVM, a positive operator valued measure? So a POVM is a family of positive semi-definite operators that are linear operators on some finite dimensional Hilbert space H, which is associated to the quantum system that one is considering, one is measuring. And these operators, this family is labeled by a set X. So you have a family of operators Px, such that each operator Px is positive semi-definite, and they sum up to identity. So they are used, this mathematical object is used in quantum theory to describe a measurement process. In particular, a measurement process of which we're only interested in the expected statistics of the measurement outcomes. So one says that if the state of the system is rho, and if we are measuring the POVM P on the state rho, then the expected probability of obtaining outcome X for each X in the set of big X here is given by the trace of rho with Px. Okay, this is also known as the Born rule of quantum theory. It is just a predictive rule to compute the expected probability of each outcome. But if we want to perform, for example, 2 measurement processes in a sequence, so one measurement after another, so take something that comes out of the measurement and perform another measurement, then in this situation, the formalism of POVMs is not enough. We need something more, because the POVM does not give you any rule about the state that is coming out, the state of the quantum system that is coming out of the measurement. So we need something more. We need a more detailed description of quantum measurement, and this is given by the concept of quantum instrument, or in particular, completely positive quantum instruments as they were introduced by Masanao Ozawa back in 1984. So we have a family of, now these are not positive semi-definite operators, but now these are completely positive linear maps from you cannot see there because there is the list of participants, or maybe it's just me seeing them anyway. So completely positive linear maps from an input Hilbert space HA, which is associated to an input quantum system, and B bounded operators, but in this case, these are just linear operators, to some output quantum space HP. And now the idea that, at the end of the day, you want to have the rule of total probability to be obeyed. This is translated for quantum instrument in a condition that the sum of these linear maps, these linear completely positive maps, gives rise to a trace preserving map. Okay, so this is how the law of total probability translates in the formalism of quantum instruments. And now the interpretation is as follows. So again, we can use a quantum instrument to predict the expected probability of each outcome. And now it's going to be the trace of this map IX applied on rho. But also we can use the formalism of quantum instruments to predict the expected post-measurement state. So given that a certain outcome is obtained, so given X in this case, then if the measurement process was described by a particular instrument IX, then the posterior state, the updated state, will be given by this formula. So then you see now we also have a post-measurement state, and so it means that we can apply another measurement on it. This is the reason why instruments are important when one wants to describe measurements that are done in a sequence. Okay, so I wanted to go back. I don't know. Okay, so let me begin with the problem of measurement sharpness. So first of all, what is the sharpness of a POV of a measurement? So sharpness is a concept that is typically introduced for POVMs. Okay, so we are not talking here about the instruments. We are only at the level of POVMs. And there are many definitions, if you want, about what a sharp POVM is, but they are kind of, it's a kind of folklore. Okay, so typically when people speak about a sharp POVM, they mean that the POVM elements are all projectors, orthogonal projectors. So you know that if you take the product of Px and Px dash, you have a delta between x and x dash and then Px. So the intuitions, so why these are called sharp? Okay, because so these POVM elements are projectors and orthogonal projectors are somehow pointed. Okay, if you touch them, they're orthogonal. You have a 90 degrees angle. So that's maybe why people call them sharp. Another possibility is that sharp POVMs or these orthogonal projective POVMs can be measured in a repeatable way. So a clear-cut way, in a sharp way. And it is the usual von Neumann-Luder's measurement postulate, right? When you have your state rho, and if a measurement outcome X is obtained, the state becomes Px rho Px. So the state is projected orthogonally on that subspace. So in this sense, they can be considered sharp because it's a measurement that if it is repeated, gives always the same result. Okay, if we assume the von Neumann-Luder's measurement postulate. So sharp seems to be a kind of good property in a sense for POVMs. And indeed, Paul Bush already in 2005 thought about the possibility of considering sharpness as a resource. And he introduced a class of sharpness measures. And more recently, there have been work by Liu and Luo in 2022 and by Mitra again in 2022. But there is an intrinsic problem with sharpness is that with this definition, we have no well-behaved class of sharpness non-increasing operations. So if you want to start considering sharpness as a resource that can be transformed, traded, or used to build a POVM or extract a POVM, you want to have a class of operations that do not create sharpness for free. Okay, so in modern terms, in resource theoretic terms, it means that you would like to have a sharpness non-increasing class of operations. The problem is there is no such a thing. Because, well, if you think about how you can transform POVMs, there are not so many things that you can do with a POVM, okay? You can do, for example, a quantum preprocessing, which is to be that before measuring your state, okay, you stick your state into some CPTP linear map, into a quantum channel, and then you perform the measurement. So this results in a pre-processing of the POVM. Another possible processing of POVM is a classical post-processing, where you look at the classical outcome that you obtained, and you consider this as the input to a classical noisy channel, represented here by probability mu. So this gives you another POVM-Q. Or you could have a convex mixture of your POVM with another fixed POVM, say some POVM-T, which means to say that you have, you have two measurement devices at hand, you flip a coin at the beginning, and then you decide whether to measure P or whether to measure T with some probability. And this gives rise in expectancy to the convex combination of these two POVMs. Or you could have, of course, a composition of all these things. So this is the thing that you can do with a POVM, but unfortunately, essentially you are stuck if you want to consider a resource theory of sharpness, because quantum preprocessing can turn non-sharp into sharp. It is possible to come up with a CPTP linear map such that its trace dual Idaga is able to transform non-projective POVM PX into a projective POVM. Okay, so you can increase. So that's not good. On the other side, also classical post-processing could turn something that is not a projector, a projective POVM, into a projective POVM. Okay, the only thing that one could say to be a safe option is to perform some convex mixture with some POVM that is maximally dull. Okay, some POVM that is not sharp at all, that contains no sharpness whatsoever. But you are in a loop now, because now you need to characterize what a maximally dull POVM is in the very first place. So it seems that there is some problem with the very definition of sharpness. And this is our proposal. So a new definition of sharpness that I call sharp-sharp. But I will not keep saying sharp-sharp because it's very confusing. So just let me say sharp. But I just put this little sharp exponent to say that this is not the usual thing that people consider as sharpness. This is a new definition, but we have reason to believe that it is the right way to think about measurement sharpness. So the definition goes as follows. So a POVM is sharp whenever the set, so the range of P, which is defined as the set of probability distributions on the outcome set that you can obtain by varying the input state, coincides with the entire probability simplex on X. And the simplex is sharp. Again, it has pointy angles. So in a sense, it's not so crazy to call a POVM sharp if it satisfies this property. And on the contrary, we say that a POVM is dull whenever its range is just a singleton. Okay, so whatever state you input in your POVM, you always get out the same probability distribution. So this definition has actually many very good properties, and it seems basically to have all the good properties that people wanted to have for a sharp measurement, even though we are some kind of distancing ourselves from the prototype of projective POVMs. Okay, and in particular, another good thing about this is that it is characterized in terms of the simplex of probability distribution. So it is not really about quantum theory. It could be applied directly to any probabilistic theory, for example. So the first property of this definition is that the POVM is sharp so you can characterize if you have a Hilbert space at hand, and if you have a representation of the POVM in terms of positive semi-Desvian operators, you can show that sharp is equivalent to saying that for any X, PX has 1 in its spectrum, the eigenvalue 1 in its spectrum. And then you can say, of course, that sharp implies, because of this property, implies that the dimension of the Hilbert space has to be at least as large as the size of the outcome set X. Okay, this because you want to have you want to have eigenvalue 1, okay, for each X. And the POVM has to sum up to identity. And so you cannot have more ones than the dimension of the Hilbert space itself. So this gives you this lower bound. So somehow you see that non-degenerate observables so like, POVM with rank 1 orthogonal elements, arise as canonical or minimal sharp POVMs. So POVMs that are sharp and whose dimension is as little as possible compatibly with the outcome space. And then excluding null POVM elements, then sharp, so this new definition is equivalent to repeatability, to the existence of a repeatable measurement process for the POVM. Okay. Instead, the usual definition of projectivity as sharpness is only sufficient for repeatability, but not necessary. So however you look at it, like even if you say, okay, we like sharp POVMs because they allow a repeatable measurement, well, then you had better go to this sharp definition, because now this is equivalent to repeatability, not only sufficient. So then equivalently, you can completely characterize dual elements as those whose elements are all proportional to the identity. So now that you have this definition, it's also possible instead to construct a complete class of sharpness non-increasing operations that in the literature are called fuzzy-fine operations, okay? So in this case, now that we have changed the definition of sharpness, now quantum preprocessing are legal, okay? Because a quantum preprocessing is a spectrum with decreasing of the operator. So if sharpness is defined as having 1 in the spectrum, if you apply a channel on the POVM, if you're lucky, you keep the 1, but typically 1 will get shrinked towards something smaller than 1. So you cannot increase sharpness of the POVM. And again, you can have a convex mixture with any dual POVM, because now we have a notion of dual POVM. So what it means is that, for example, sharpness non-increasing operations could be seen as this, that you start with a quantum system, you flip a coin with probability lambda, and then depending on the coin toss, you perform your measurement and maybe you apply a channel before it, or you just throw away your system and you toss you throw a classical dice to have outcome X, okay? And this as a black box is again a POVM, which is a convex mixture of EDAG applied on PX and the dual POVM, okay? So this is a way to represent fuzzy-fine operations as affine maps. Okay, this map is not linear, of course, because you have the term in identity here, but is affine. So it preserves, it behaves well under affine combinations of inputs. But you can also turn that into a linear transformation, because linear transformations are easier to understand and to consider. In this case, however, you have to consider an extended object, so which is not only your POVM P here, but it also has X many other trivial POVMs, which are the POVMs that always output a definite outcome anytime. So for example, T2 will always output outcome 2. T1 is the POVM that will always output 1, okay? And so on and so forth. So you have X plus 1 POVMs here, and you have a program that chooses between these POVMs. So now fuzzy-fine operations can be seen as, acting on this bipartite object, which is a programmable POVM with a quantum input and a classical input, which is the program. And then you have some quantum preprocessing here on the quantum input, some classical preprocessing here on the classical input to the program. And then these two boxes could be correlated by, for example, classical randomness, right? So there is this R. So if you put everything in a black box, you can also look upon fuzzy-fine operations as local operations with shared randomness, essentially, right? Because now you have a bipartite object. And then you can also consider the sharpness preorder now, because you have a well-defined preorder. Right? I give you a set of operations, and using this, you can introduce the order as follows. So you can say that the POVMP is
林先生。まあいいか。
そうね、10分ぐらいずらすか。
あ、そっか。
Oh, now you are recover? Okay.
Yes, seems like.
Network of Nagoya University, entire Nagoya University was done. And now, perhaps it's okay. So, can we continue or should we reschedule this talk?
No, we can continue. I
No,
think.
please continue, please continue.
10 minutes maybe. Yeah. Okay.
Okay.
Thank you very much. Okay. So, so, can you hear me? Yeah, I think so. Okay, so now that we have that the theory of, well, the concept, the very concept of measurement sharpness has been turned into a well-defined preorder, then one can study the preorder instead, okay? So now you can ask, for example, what are the maximal points for this preorder induced by sharpness non-increasing operations? What is a maximal point? Are points P such that if P is majorized by some other P of M Q, then necessarily P is also able to majorize Q itself. Okay, so in this sense, they are maximal, that they are not strictly majorized by any other element. And these elements that are maximal for this preorder are what we call the sharp P of M. So everything is very consistent now. And the same happens with dual P of M's, which happens to be the minimal points. So points that are that cannot strictly majorize any argument. Okay, so it means that all sharp P of M are equivalent to each other. So if you start from a sharp P of M, you can obtain any other P of M with a fuzzyfying operation. And if you go to a sharp P of M, you can also go back. And also the same is for dual P of M. So essentially you can say that you can choose one maximally sharp P of M. So you can have a kind of a golden stardom for sharpness, as it happens with bipartite entanglement. So now, formulated in this way, this has become a problem of statistical comparison in the Blackwell sense. And so then you can apply all the techniques that we know also to work out a complete family of monotones that completely characterize the existence of a sharpness not increasing transformation between two P of M and so on and so forth. But this I leave only to interested readers in this paper. Instead, I would like to move on to the second part of this talk, which is about the problem of compatibility for quantum measurement. So incompatibility is important. Incompatibility in the sense that in quantum theory, there exist measurements that necessarily exclude others. Okay. So for example, if you measure position, then you have somehow to give up your knowledge about momentum in a sense, right? So in this sense, they exclude each other. So in particular, in this talk, we will not work with measurement and with position and momentum because we will be in finite dimensions, but still you can say the same things, for example, for spin measurements in orthogonal directions, right? And incompatibility is a feature of quantum theory. We would violations of the qualities, we wouldn't have quantum speedups. So there essentially would be no separation between quantum theory classes. And it is for the existence of measurement incompatibility, which can be given in terms of preparations uncertainty relations, like Robertson inequality, or measurement uncertainty relations, like Ozawa uncertainty relation, Ozawa inequalities. But in this talk, instead focus on the algebraic characterization of incompatibility. which is the following. So we start from the case of P of M. So for P of M, everyone agrees that the right definition, the correct notion of compatibility is encapsulated in the following definition. So now the object of interest is not one P of M, but of course it's a family of P of M's, because we want to say when this family is compatible or not. So it's not just one P of M, but it's a family of P of M's PI, all defined on the same system. So we say that this family is compatible whenever there exists a mother P of M O. So now this is just one P of M. And now we have a condensate distribution labeled by I, which is the index of the family, that W, which is the output of the mother, such that all P of M elements in the whole family that we are considering can be obtained by just taking the outcome of this fixed mother P of M measurement and then process this outcome with some classical noisy channel. Okay, so but what does it mean operationally if I say this? For example, if I say that a certain laboratory can only perform compatible measurement, what does it mean? Like operationally, how is this laboratory made? Are there some walls somewhere? Is that you can always say a posteriori that, okay, this laboratory will not able to have any quantum advantage with respect to a classical computer simulated measurement, right? But operationally, how can we say something about this laboratory? Okay, so, and this brings me to the idea that in fact there is a bipartition hidden in the concept of incompatibility, because you can imagine the following situation. So you have a family of P of M. So it means that actually there are two inputs there. There is a quantum input, which is the state that you measure, and then there is the classical input, which is the program that chooses which P of M in the family is going to be measured. Okay, so you can imagine that the quantum input is the system A, and then we have the classical program I. And now the quantum input and the classical program are given to two separate parties, okay? So that one party knows only the quantum input and the other party only knows the which P of M information. And the communication can only go this way. Okay, so it means that, if you are in a laboratory that can only output can only measure compatible P of M's, it means that at some point there is a bottleneck of this sort, where you have just a fixed quantum measurement and then just classical information being forwarded for classical processing. This could be enclosed in a black box, okay? But if you open the black box, you will always be able to see this, because on one side, it is clear that if you are in such a situation, then all P of M families that can be obtained with this structure are compatible, right? Because there is only just one mother P of M O. Vice versa, if I give you a compatible family of P of M's, because of the definition, you know that there exists a mother P of M, and there exists a stochastic post-processing mu, and you can arrange the two things in this way, okay? So there is a notion essentially of one-way classical communication. So now, the problem with incompatibility is when we go to the level of instruments. So for P of M's, I would say that the problem is settled, but when we go to the situation of instruments, we find a debate, actually arguments in the literature. So the first definition of compatibility for instrument is this one, which is called classical compatibility, which is as follows. So now I give you a family of instruments, and we say that this family is classically compatible whenever there exists a mother instrument, HW. So W again is the classical outcome of the instrument, and H is the map itself, and a conditional probability distribution mu, a stochastic post-processing mu, such that all maps in the family, okay, of instruments can be obtained by some suitable classical post-processing of the mother instrument, okay? And if you draw it, it's like this. So you see why this is kind of the straightforward extension to instrument of the compatibility of P of M's, right? The structure is exactly the same. It is just so that there is a extra output system coming out of the mother instrument. But nothing changes. And in particular, you see that by the way in which these arrows are arranged, you see that there is communication going only from 1 to 2, from the quantum program, say Alice, to the classical program person, okay? And so there is no communication from 2 to 1. So in this situation, you have a box that is necessarily 2 to 1 no signaling, or a semi-causal box. And this has been considered as a very important point of this definition of classical incompatibility, which relates compatibility with no signaling bipartite correlations. And then you can leverage about everything that we know about bipartite no signaling correlation. And this was done, for example, by G and Chitamber a couple of years ago. But there is also another notion of compatibility that comes from the understanding that compatibility of POVM can be also seen as a marginalization strategy, right? In the original definition, I gave you a stochastic processing, post-processing, like a classical noisy channel. But actually, because what you're working on is just a classical label, you can imagine that, okay, first I make many copies of the classical label, and then I apply post-processing on each label, so that at the end of the day, I can say that I can basically restrict without loss of generality to a post-processing, which is just marginalization over classical outcomes, okay? So bringing this intuition to the level of instrument, we have the notion of parallel compatibility, which is defined as follows. So now, again, a family of instrument, now we say that this family is parallelly compatible whenever there exists a mother instrument that you see takes the input system A and then outputs the tensor product simultaneously, the tensor product of all output systems. And then you have a conditional probability distribution such that each instrument can be obtained by taking the partial trace of the mother and then doing some post-processing on the outcome. So if you draw, well, the situation is as follows, okay? So now the big difference is that now you have one round of classical communication going from the classical program to the quantum system as well. And here you have all these systems BI being output at the same time in parallel. This is why it's called parallel compatibility. And only at the end, you choose which one you want to look at, okay? So the problem is that now these two definitions of incompatibility are, sorry for the pun, incompatible, because okay, here you have classical compatibility on the left and you have parallel compatibility on the right. So first of all, in the case in which the mother instrument has no quantum output, so in the case in which you are essentially specializing to POVM, they both agree and they give you back the original definition of POVM compatibility. However, for instruments, they disagree, and they disagree in a way that cannot be saved, okay? Because parallel compatibility has one more round of communication. So you can have communication also from 2 to 1, okay? So it means that a parallelly compatible family need not be classically compatible, because classical compatibility is necessarily non-signaling, right? On the other hand, according to the notion of parallel compatibility, non-disturbing instruments are never parallelly compatible. What I mean is, say, suppose you have two instruments, okay? Neither of them actually does anything on your system, okay? So you just keeps the state there, sitting idle, and just flips a coin, okay? You have two such trivial measurements that carry no information, but also cause no disturbance on your state. So now if you wanted to implement them in a parallel fashion, it means that you would be doing perfect cloning, right? Because it means that you would be able to output both non-disturbing instruments at the same time, thus causing a perfect broadcasting of quantum information, which is not possible, right? So by its very definition, non-disturbing instruments can never be parallelly compatible. However, they will be trivially classically compatible because it is just doing nothing, right? So you don't even need a mother instrument at all. So it means that you are just in a situation where parallel compatibility and classical compatibility are just inequivalent notions, definitions of instrument incompatibility. So we are in a very bad situation here because now what we are talking about, it just boils down to matter of taste. This cannot be the case, right? I mean, if we are doing mathematics. So is there something that captures both notions? And this is our proposal, the notion of Q compatibility, okay? So given a family of instrument, we say that the family is quantum compatible whenever there exists a mother instrument, a conditional probability distribution, and a family of post-processing channels, now, not just partial traces, such that this happens. So I think it's best seen as a picture. So the picture, if you look at it, is clearly in the form of parallel compatibility. The only difference now is that you have a system C in between, which need not be the tensor product of all the outputs, and a post-processing channel D, which need not be a partial trace, okay? But apart from that, the situation is the same. So it is clear that quantum compatibility comprises classical compatibility as a special case when there is just one output here, and then these post-processing here are all fixed, okay? There is nothing here. Or parallel compatibility, when here you have this C to be the tensor product of all the outputs, and this channel D to be the partial traces. So basically, this solves the problem and also allows you to understand which kind of instruments processings are the good one if you construct a resource theory of incompatibility, right? So now you have various layers of instrument incompatibility, and Q compatibility or Q incompatibility is somehow the most general transformation, and you can apply on a family of instruments seen as bipartite boxes with a quantum input, a classical input, and then a quantum output and a classical output. So you want to process a bipartite channel into another bipartite channel in a way that compatibility is preserved. So in a way in which incompatibility cannot be created for free. So this would be the setup in the case of classical incompatibility, and this is the setup instead in the case of quantum Q incompatibility, right? You see that your initial resource here is sitting in the middle, and you surround it by this network, which is arranged in such a way as not to break the directionality of the classical communication. Okay, and again, you can introduce a pre-order now because you have a set of pre-operation. And again, then you can see that this becomes a problem in statistical comparison, and we again can apply the techniques that we know. Okay, so this brings me to my conclusion. So take-home messages. So about sharpness. So with this new definition that I proposed to you, so this sharp, which is about the polytope of probability distributions, not about the operators themselves. So we now have a sound resource theory of sharpness, complete with a family of sharpness on increasing operations and sharpness monotones. I didn't present the monotones here, but we have them. And they are also very nice to see. They are not strange functions. They're just kind of correlation functions. Sharpness then is essentially a measure of classical communication capacity, right? So it's sharp if you can transmit, the entire probability polytope through your channel, right? So sharpness becomes essentially capacity, communication capacity. On the other hand, about incompatibility, we've seen that we do not need to argue about which is the correct definition of compatibility for instruments. Before there was classical incompatibility, parallel incompatibility, and people have been writing papers arguing that one is the correct one and the other is the wrong one. But this doesn't make much sense as a discussion, in my opinion. Instead, it is interesting to try to find out a larger umbrella that takes into consideration both of them. And this is what we achieve with this notion of Q compatibility. And then we also understood that incompatibility is an essentially non-local concept. It is about quantum information communication from the quantum system to the program. And this communication can happen in space or in time. So incompatibility is not a local concept, but it is always something about quantum communication. Okay, and I thank you for your attention.
Some question or comment?
I'm Hayato Arai from Nagoya University. Thank you for your interesting talk. So, okay, please go back to the page 8. So you focus on the simulable probabilistic vectors with all states. So can you generalize the definition of sharpness by restricting the states to some class of states, so-called free states, sub-free states in some resource theory?
But here the important thing is that sharpness is defined as the entire probability simplex, right? So if you want a simplex, then you can say, okay, I just, so I mean, if the family of state is itself a polytope, perhaps, you know, then I can say, okay, then I define my measurements as all linear maps on those states. So at each vertex, I can say that there exists a measurement that gives me probability 1 on that vertex, right? So in that case, it would be sharp, yes. If instead you say, okay, I restrict my theory in such a way that there are no, you know, I restrict both states and measurements in such a way that there are no perfectly distinguishable states, then I don't know, one should think about it. But of course, the definition in that case should be modified.
So if possible, so we can consider some integrated resource theory of measurement resource and state resources. So I'm interested in
yes, that is a good
direction.
idea. Definitely. Yes,
Thank you.
Thank you so much. We can discuss about it.
I'm Ansis Rosmanis from Nagoya University. Maybe that's what you meant by these sharpness monotones, but is there some kind of way to measure, to like assign a number?
Yeah.
So that's
for example, a simple monotone would be to take the sum of the trace of the square of each px. So say sigma x trace of px to the 2. Okay, if the px are projectors, for example, you see that px to the square is equal to px, the sum is identity, so you get a d. If they're not projectors, then this number would be smaller than, and it would be smaller than d. So this is one particular monotone. The point is that if you want to really decide whether you can transform one P of M into another by means of this sharpness non-increasing operations, then one monotone will not be enough. Okay, these are big objects with a lot of dimensions, so you want to have a lot of monotones to check. So in our formalism, you have infinitely many such monotones, unfortunately. But it could be, for example, that in an asymptotic situation, like, for example, there are many situations in which if you're interested in the exact one-shot transformation from one object to another, you need an infinite set of monotones. But if you're interested in an asymptotic sense, the transformation, then maybe one monotone might be enough. Just one function might be enough. But we haven't gone at all into the asymptotic setting, so it's completely open.
Thanks.
Some question or comment? Some question or comment from Zoom? Oh. Okay. Let's thank speaker again. Hayashi Sensei,
Yes.
should we start the next talk now
Yes,
or?
please start.
Ah.
Next speaker is Shintaro Minagawa from Nagoya University.
So thank you for introduction. I'm Shintaro Minagawa from Nagoya University, and I'd like to thank the organizers for inviting me to this workshop and giving me opportunity to talk this our recent work, the second law of information thermodynamics for general measurement processes. This is a joint work with Kenta Sakai, Kotaro Kato, and Francesco Bushin. And this talk is based on the archive paper here. So if you want to know more detail, please read this article. So the motivation of our work is Maxwell's demon paradox. So prepare two types of gas in a separated room. And if we remove this ball, they mix spontaneously because of the molecular's motion. And the backward process does not occur spontaneously. So the right-hand side is higher entropy. So this irreversibility means that the entropy non-decreasing law or one of the representation of the second law of thermodynamics. But if we implement a measurement to each particle and if we identify which types of gas, then make a feedback control, one can implement a backward process which does not occur spontaneously. So feedback control can decrease the entropy. And how to make feedback control and the second law consistent is one of the biggest problem in foundations of statistical mechanics called Maxwell's demons paradox. And one of the acceptable solutions of this problem is Saga and Ueda's two papers. So first, 2008 paper, they show that feedback control allows us to extract more work beyond the conventional second law. However, in a subsequent paper in 2009, they show that the work feedback controller needs for the measurement and resetting its memory, in other words, erasure, compensates that excess, and the conventional second law recovers. But the analysis by Saga and Ueda has a problem that the measurement process they deal with is not general. So as figure 2 indicates, Saga and Ueda's analysis does not cover the full range of feedback control and erasure protocol with all quantum measurement processes. And also, they impose several assumptions and show the consistency between the second law. So they only provide the sufficient, not necessary condition for the feedback control and erasure protocol to be consistent with the second law. What we would like to do here is to completely characterize this region. So not only providing the sufficient, but also necessary condition for the feedback control to be consistent with the second law of thermodynamics. But before we argue the second law of thermodynamics, we would like to explain the first law of thermodynamics. So consider the gas in a cylinder, and this is a piston. So the first law means that the internal energy change due to heat and work added to the system. In the formula, internal energy change is equal to the heat added to this system and the work added to this system. This is a kind of the energy conservation law, but in a thermodynamic narrative, we call this the first law of thermodynamics. Then we explain the second law of thermodynamics. So second law has various expressions which are equivalent, but we would like to focus on this inequality. So consider the system in a system is surrounded by the environment, and this system changes by observing the heat from the environment, and maybe added some work. And we define the Helmholtz free energy like this one. So F is equal to internal energy minus temperature and entropy of the system. So since we are considering the isothermal processes, the free energy change is equal to so internal energy change minus the environment temperature and entropy change. And we assume the first law, and we omit the proof, but we have the Clausius inequality like this one. So then, if we combine these relationships, we obtain that the work we need to add this problem is not smaller than the free energy change, or if we make the sign opposite, the work we can extract from this process does not exceed the free energy reduction. So since this inequality comes from Clausius inequality, we also refer to this inequality as a Clausius type inequality. So now we proceed the basic notions of this presentation. So the name of the target system we are focusing on is A, and its Hamiltonian is HA. And this is the average energy. Here, rho A is a quantum state. And then this is the inverse temperature, which is a strictly positive value. And this is a partition function. And this is a Gibbs or thermal equilibrium state defined by this one. And this is an equilibrium free energy. And this is a fundamental entropy. And note that here the base of logarithm is not 2, the Napier number. And also we define the omega key relative entropy for invertible matrix sigma A like this one. And this is a quantum mutual information. And we the main quantity we use here is a non-equilibrium free energy, which is defined by the equilibrium free energy plus the beta inverse of omega key relative entropy. So we frequently use the important formula like this one. So free energy is non-equilibrium free energy is equal to the averaged energy minus beta inverse of von Neumann entropy. Then next, we would like to explain the quantum instrument. So we just explain the quantum instrument. So this is the quantum state law, and if we implement the measurement to the quantum state law, then we obtain the measurement outcome K with a probability Pk, and this is a post-measurement state of the when we obtain the measurement outcome K. So here, MK is a CP, completely positive linear map, and MK, if we take the summation of the MK, then it becomes a trace preserving. And it is known that this quantum instrument can be physically realized by indirect measurement scheme, but we use the formalism of quantum instrument as a general measurement processes. So we say that the instrument M is efficient if Mk has only one Clausius operator for each measurement outcome K. And we define the Grunwald-Ozawa information gain, which is defined by this equality. Here, SA is the entropy of the before the measurement state, and this one is the entropy of the post-measurement state, but conditioned by the classical measurement outcome. And similar quantity, but completely different quantity, there is a QC mutual information, which is defined as this one. So it is, so here EK is a POBM, and this is a post-measurement state of the square root instrument. So it is known that for efficient instrument, Grunwald-Ozawa information gain is equal to the QC mutual information, but here we do not have a specific reason to so restrict the measurement processes as efficient. So we mainly use the Grunwald-Ozawa information gain. So then we would like to go to our first main result. So we consider the general setup of work for controller-assisted information processing, like this circuit. So first, we prepare the target state rho 0A, and this is a controller state, sigma 0C, and this is the thermal state of the bus. So first, from the time step T0 to T1, we implement CPTP map D to the target state A and controller state. And then we obtain a bipartite state. And after that, so from the time step T1 to T2, we implement a unitary interaction between only the controller and the bus V. And finally, we obtain tripartite state omega 2. So in this case, in this situation, we would like to consider the work. So first, we define the work we can extract from the target system. This is just energy reduction during the time step T0, T1 with respect to the target system A. And next, we would like to consider the work cost to implement this unitary. So here we use the first law. We assume the first law during the time step T1 to T2. Which is equal to this one. So the energy change of the controller is due to the work due to the controller and heat absorbed by the system. Here, heat absorbed by the system is equal to the energy reduction of the thermal bus. So then we obtain that the work cost we need to add to this process B is equal to the energy change of the controller and bus from the time step T1 to T2. Okay, so then this is the work we defined, and then the total work cost we need to add the controller is equal to the energy change of the controller from the time step T0 to T1 and this one. And finally, we define that the network we can extract from the target and the controller is defined as the work we can extract from the target system minus work we need to run the controller. Then we focus on this, the network we can extract from this information processing. Okay, so we also define the mutual information increasing between the target system and the controller from the time step T1 to T2, like this one. And this is not positive because of the data processing inequality. And also, this is a mutual information between the controller and the bus, so with respect to the final state. And this is a relative entropy, which indicates that how much difference occurs with respect to the thermal bus. Okay, so we omit the proof, but we obtain the work formula. The network we can extract from this information processing is equal to this one. Then we obtain the first, our main result. So we explain that the Clausius type inequality means that the work we can extract it does not exceed the free energy reduction. So this inequality holds if and only if these four terms are non-negative. So then we obtain this equivalent condition of the Clausius type inequality. So this seems a little bit complicated, but we know that the minus of the delta I and the D are non-negative. So when the delta SAC 0 to 1, which means that how much entropy increasing occurs during this D is non-negative, then this inequality automatically holds. So now we would like to apply our general setup to the feedback control and erasure protocol, like this circuit. So consider we prepare the target state rho 0A, and this is a Maxwell's Damon's memory. And this is a classical register which is used for keeping the measurement outcome K, measurement outcome. And this is a thermal bus. And from the time step T0 to T1, we implement a unitary interaction U to the target system and the Maxwell's Demon. And after that, we implement a general measurement process M to the Maxwell's Demon's memory. And if we obtain the outcome K, then we implement a feedback control as a controlled unitary UK based on the measurement outcome K. And this is the final unitary. And this this unitary makes the Maxwell's Demon state is equal to the initial state, and also the classical register state as the same as the initial state, which means that erasure is achieved. So if we regard this blue shaded box as a CPTP map D in the previous setup, we can directly apply the theorem 1 result to this feedback control and erasure protocol by just rephrasing the controller as a Maxwell demo and classical register. And if we also properly rephrasing the time step, for example, T2 to T4 and T1 to T3. Then the theorem 2 means that the necessary and sufficient condition for the Clausius type inequality holds in the feedback control and erasure protocol. And yeah, minus delta I and D are non-negative. So if this first term is non-negative, this inequality holds. The first term means that entropy increasing during the measurement process. So finally, we would like to proceed the generalized second law of information thermodynamics. So in this section, we mainly focus on the work we can extract from the target system and work cost we need to add the controller. So we also omit the proof, but we obtain the work formula for the work extracted from the system like this one in this setup. And yeah, so if we apply this formula to this setup by properly rephrasing the time step and time step. So for example, the free energy change is equal to this one in this setup, and also entropy change is this setup. And the entropy increasing from entropy change from the time step T0 to T3 is equal to this one. If we use the non-negativity of the mutual information, we obtain this inequality. So finally, we obtain the theorem 3, which means that the work we can extract from this information processing does not exceed this one. Here, the second term is equal to the ground world. Second term is equal to this one, and ground world of our information gain. And we also have a work formula of the controller like this one. So we also omit the proof, but we obtain this one in this setup. And also, if we properly rephrasing the setup to this the feedback control and the erasure protocol, and if we use the strong subadditivity of von Neumann entropy, we obtain this inequality. Okay. So in summary, we obtain the general inequality. So the two inequalities, which is valid for general measurement processes. So first one is this one and this one. So now we assume that if the measurement process here is entropy non-reducing, then we have this one, this inequality. And combining this inequality and this first inequality, we obtain a generalized second law of information thermodynamics, which means that the network we can extract from the this information processing does not exceed the free energy reduction of the target system. But in what sense so this argument is generalized? So we compare our result and Saga and Ueda's previous result. So yeah, our result is this two inequality, and Saga and Ueda's inequalities are these two inequalities. So there are three differences between our result and Saga and Ueda's result. So first one is here is free energy, non-equilibrium free energy change, but this is an equilibrium free energy change. And this is the IGO, but this is the IQC. And this inequality does not contain this term. But Saga and Ueda's, so if we impose the Saga and Ueda's assumption to our general setup, we can reproduce the Saga and Ueda's result. So since Saga and Ueda assume that M is a projection, then the entropy does not reduce during the measurement processes. And also, they assume that the target system's measurement process is efficient. So then, ground world of our information gain is equal to the QC initial information. And also, they assume that the target system's initial state is a given state. Then we obtain this inequality. So combining these result and this our general inequalities, then we directly obtain the Saga and Ueda's result. And there is a generalization of the Saga and Ueda's result by Abdel Khalif et al.'s paper. They only assume that the M is a projection. So then the entropy non-reducing during the measurement processing. So combining this inequality and our general inequalities, then we obtain the second law of information thermodynamics. So I would like to conclude my talk. So we analyze the work associated with the feedback control with a general quantum measurement process. And we obtain the necessary and sufficient condition for the Clausius type inequality like this one. And we obtain the two bounds of work which hold in general measurement process like these two inequalities. And finally, if we assume that entropy non-reducing measurement, then the second law of information thermodynamics can be obtained. So thank you very much for listening to my talk.
Question or comment?
So I have a question. So I could not understand the formulation. Could you back the part for formulation of your problem setting?
So problem setting is this one or this one or so which one is
So part is A and part is M. So you consider several systems, but I cannot understand the definition of each system. So part is B, part is V.
okay. So D is a CPTP map.
No. First, you need to explain what is ACD.
So okay. So, A is a target systems. We would like to implement or some control. So feedback control or some and measurement. So this is a target system. We would like to make a feedback control, and this is a controller which drives this feedback control. And this is a thermal state of the bus with a some Hamiltonian and inverse temperature.
I cannot understand your problem setting. So there is a bus B. From bus, you want to extract some work.
Okay. So first, so we define the work we can extract from the target system is like this one. This is just the energy reduction during this time step T0 to T1. So yeah, there are a lot of work definition, but yeah, first one is this one. And next,
please explain definition work. So you want to extract work from system B. B
okay.
is
So this is a work. So the extractable work is just an energy reduction, but this comes from maybe from for example the controller or another system. But yeah, this so we just define this work. Okay. なんかそもそも僕ズームから落ちちゃってます。
何なんだ、今日はもう良くないな。
なるほど。声を伝えて。
なしでも説明して、あとちょっと待って。
そうです。ちょっと。
つなげなくていいです。
はい。So the work we can extract is from the target, just energy reduction. But also we.
So I cannot show your slide.
So I will show.
But I think it takes time. So and we are running behind schedule. So is it okay?
So maybe you can see my slide. So
B is bus and A is
yeah. So the next one, we would like to consider the work. We need to run this controller. So this is due to the first law of thermodynamics. Then we can obtain this. The work cost we need to run this controller.
This is too abstract, so I cannot understand. What is work? In order to define work, maybe
Yes.
you have some another system. So another system get some positive energy. So
Yes.
so what is another system? This is A.
So we do not explicitly write another system because, so for example, if we properly implement a battery system, and we can obtain the work by implementing this unitary, but we do not explicitly introduce the battery system, which is used for the work extraction. So, but yeah, so yeah, if we.
I could not understand.
Oh, okay. So maybe it would be.
This is too abstract. So because, for example, my previous work, I explicitly write down everything, and also we consider the finiteness of each system. But you consider that the size of you don't care about the finiteness of God. How do you treat the bus? Sometimes some people consider that the size of a bus is infinity, so we could not consider that finiteness of B. So how is your case?
Yeah, so we do not assume the dimension or size of the bus. So yeah, this is just a Hamiltonian bus, Hamiltonian inverse temper. So the
so in that case, if you extract the energy, so in that case, the energy of bus is decreased if you consider finiteness. But maybe you don't consider that situation. Maybe you assume that B is the size of B is infinitely large.
So yeah, but so we are so we consider that so here so the bus is the thermal state, but after the unitary interaction, so the bus is not necessarily the so the thermal equilibrium state. So we do not so assume the dimension. So then the gamma B can be changed during this process. So we do not assume anything about the thermal bus. Yeah.
Anything? I cannot understand. So quite strange. So the result is completely different from ours, and setting is completely different. So quite difficult to compare.
Okay, I see. So.
And usually, if we care about the finiteness, the problem analysis is much more complicated. Only that kind of entropic analysis is not useful. So we need to consider more information theoretic analysis if you care about the finiteness of a system. So if you consider some system is infinity, so in that case, the problem setting becomes much easier.
Okay. So I understand. So, yeah.
But you did not write down everything, so then quite difficult to understand. So you discuss so many things later part, but in this part you write down, and also quite difficult. You consider where is measurement, what is the role of measurement in your setting?
Yeah. So
M is measurement.
So M is so we would like to measure the target system state by such a kind of indirect measurement. So by indirectly measure the target system by measuring the Maxwell-Demon's memory. So U interaction, and this is a measurement. But we have to also care about the post-measurement state, not only the target system, but also the Maxwell-Demon's memory. So here this M is a general instrument. And then if you obtain the outcome K, then we implement the feedback control to the target system as a controlled unitary. So yeah, so
still I cannot understand what is A and what is M and what is B. So where's the battery?
So we also omit the battery, but yeah,
But without battery, how to define the work extraction?
Since this blue shaded box is adiabatic, so the energy change can be regarded as a work we can extract.
Energy change. Which part of energy change?
So energy change is due to the information. So for example, the target. So if we change the target state, then we can obtain. So the
Energy of which system? Energy of which system?
Energy. So the work we can extract from the target system A is the energy change of the target system A.
Work is defined as the energy change of system A.
Yes.
And B is battery.
Yeah, we do not impose the battery. So just regarding the energy change as a work. So
B is A, but A contain battery, something. I cannot understand it.
Oh, I see. So
B is battery.
B is a thermal bus. Sorry. So
B is thermal bus. So thermal bus. So using the energy difference, but this is too abstract. So why you can extract the energy? So because usually there is energy move from B to A, so then you can obtain some work extraction.
yes.
There is no interaction between the B and A.
Yeah, but so during the time step T0 to T3, there is no interaction. But since this blue shaded box does not touch the thermal bus, so this is we say that this is adiabatic information processing. So yeah, so in this case, we do not consider the heat or just energy change as a work. Sorry.
Still, I cannot understand why there is a operation in V after
V, yes.
I cannot understand. So, what is the role of bus?
So the role of the bus is just a thermal. So since concerning the Maxwell's demons problem, so they consider that the Maxwell's demon interacted with the thermal bus after the feedback control. So then it goes back to the initial state, which means that erasure.
In order to make erasure, you need to use thermal bus.
So here we consider such a case. Yes.
So essentially, work extraction, where you have you realize a work extraction. So system A and system M, I cannot understand. So A and M, but M is only some other system, control system. So M is controlling.
So it is known that if we properly introduce a battery, then we can implement a unitary interaction to unitary operation, and we can extract our work. But here we do not explicitly implement.
So you consider that work extraction process can be written by only unitary. You consider this way.
Okay. So this unitary is okay. So yeah, but
no, not V, maybe you.
You are here.
You are UK make some unitary to make work extraction. So this is your idea. So you consider that work extraction can be written as a unitary process. Okay?
Yes, okay. Yeah.
But we disprove that statement in another paper, in our paper. Unitary operation does not describe the work extraction process.
Oh, I see. Yes. So
of course, before our paper, many people consider that that unitary exists. Work extraction process can be written with unitary, but we disprove that statement in our paper, and later another paper also discuss that same statement, but later paper has more citation than ours.
Okay, I see. So yeah, so here we also so this is a unitary, but here we also consider that.
Of course, Professor Sagawa considered in that way. He believed that the process can be written by unitary process, and I and Tajima, and mainly Tajima, explained this is not true. So, but he did not agree in that statement. But Professor 誰だっけHaru Tasaki, he agree our statement.
Okay, so I see. So maybe you think that so we need to explicitly write how to extract our work. I see. So yeah, in our paper also we do not introduce explicit battery. So yeah, okay. So maybe this is. Thank you very much for your comment and advice.
Sorry, I make so long discussion. Sorry, I stopped now.
So let's thank speaker again. And then next speaker is Masahito Hayashi.
Okay, I will start. どうしよう。これじゃなくてこっち。Hello, can you hear me?
Yes,
So, can I start?
please.
Okay. Today I talk about our recent result, tight Kramerau type bound for multi-parameter quantum methodology. This is my joint work with Professor In-Kai Ouyang. Now he belongs to University of Sheffield, but mainly this work done when he belonged to University of National University of Singapore, NUS, and CQT, Center for Quantum Technology. This paper is on archive, but recently this paper is accepted and already published from Quantum, Journal Quantum. This is a very traditional problem. This is the motivation of this topic is back to my master thesis, maybe 1996. This is very old topic. Of course, many people, already Professor Oreb considered that problem many years ago, but the approach of that problem is studied in my master thesis. This is very old idea. So, how to say, so maybe this is, firstly, we want to consider state estimation. This is rho theta. Depending on theta is parameter. Usually theta is this way, set of parameter space. This is somehow linear vector, real vector, and in this way, this one. And D is the number of parameters. So we assume that the density matrix is parameterized by theta. So of course we assume that some continuous condition. And we can consider its partial derivative. So we have a D parameter, then we have each partial derivative, and also we assume that at some point, this is linearly independent. So, and state estimation somehow contradictory. So theory of state estimation is somehow quite strange. Usually we don't know where the true parameter, but always we need to discuss this partial derivative only at one point. So we need to estimate the true parameter, but the parameter precision of that parameter estimation depends on the true parameter. So due to that reason, we always consider that partial derivative at some fixed point. So then we can evaluate the performance for the state estimation when true parameter is some fixed point theta 0. So in this way, error of precision depends on the true parameter, even though we make some good estimator. So we want to make estimate with very small error. So then we need to define the measure of error. Because we have a not unique parameter, so if you have a one parameter, it is enough to consider mean square error for the fixed one parameter. So maybe it is considered that this is only one. So, but of course, this is okay. I forget the important things. To make that estimation, usually we make P of M measurement. So depending on the measurement outcome, so we need to make outcome theta hat. So firstly, you make a measurement. So then you have an outcome X. But depending on X, you need to choose the true parameter theta hat. This is vector, so then theta hat I. So but this one is true. So we need to consider its difference. Of course, this one is j equal to I. So then this one shows that the mean square error for the ith parameter if j equals I. But now we want to consider plural, so several parameters. So in that case, we need to consider mean square error matrix. If this average equal to the true parameter, in that case, this is covariance matrix. But covariance matrix meaning only when true parameter equal to the average of that estimate. So if the average of theta equal to this guy, so in that case, this one is covariance matrix. But this is not true in general. So then we need to consider that mean square error matrix. This is a kind of generalization of the covariance matrix. So we consider this one. And this is a measure of our precision of estimator. Of course, this is not a single real number. This is somehow symmetric matrix. So the set of symmetric matrix is not full ordered. So then it is quite difficult. Which one is better? So some estimator is very nice only for the first parameter, but some estimator is very nice for the second parameter. So in that case, you cannot directly compare these two estimators. So in order to resolve that problem, we need to make some full order case. So in order to make this way, you need to introduce weighted matrix G. So for example, if G is a diagonal matrix, so this is only the direct weighted sum of the mean square error for each parameter. And this is generalization of that kind of weighted sum of mean square error for every parameter. So we consider this value. So we take trace. So then this is real number. Then we have a full order. So full order. So then we can relatively easily optimize this quantity. So, but it is not so easy to fully optimize that problem. So usually we consider this kind of somehow artificial problem because the state estimation is enough to consider local state estimation problem. Because we can make some two-step strategy. So then finally, the problem of state estimation reduced to the local problem. Local problem means that we consider true parameter is close to the parameter theta. And somehow...
So, Professor Hayashi,
Yes?
Can you hear me?
Yes?
Well, our networking started wrong with some problem. So we cannot hear your voice for a few minutes.
Oh.
So now we repair the network system. So maybe soon we can recover. So please wait for presentation.
Speaker?
Yes?
はい、先生。The network of Nagoya University was.
聞こえてますか？
はいはい。OK, yes, yes.
Can you, from page 3? Maybe. Can we start from page 3?
Page 3, okay. Okay, I restart. Okay, now I explain again. So we consider how to measure our error for each our estimate. So estimation process described by two steps. Firstly, you need to make measurement. So P of M make describe the measurement process. And second, depend on the sorry, maybe it is better to full screen mode. So, so firstly, we make measurement by described by P of M, and we obtain outcome X. Depending on X, we need to decide the our estimate theta hat. So theta hat X describes that function. So, but our error is different from the true parameter theta I. So if this j equal to I, this amount is mean square error for the ith parameter. And if this average of this one equal to true parameter, so this one also equal to the variance. But now we want to consider a more generic case. So if this one average of theta I equal to theta I, theta hat I, average of theta hat I equal to theta I. So in that case, this one give the covariance matrix. So, but that kind of condition does not hold in general. So then we consider alternative case. We call this is mean square error matrix. So if we only one parameter, this is mean square, but we have this various parameters. So then we have a mean square matrix, mean square error matrix. So off diagonal part is given this I not equal to j. So, however, this is not full ordered because the set because this mean square error matrix is a symmetric matrix, and the set of symmetric matrix is not full ordered. So then, if for example, some estimate is very nice for first parameter, and this one is not so good for second parameter, and another estimate very nice for second parameter, but this is not so good for the first parameter. So in order to handle that trade-off, we need to make some weighted sum. To discuss that weighted sum, we consider weighted matrix G. This is another positive semi-definite matrix, and you take that trace product of this matrix and take trace. So we minimize this quantity. So our criteria is given this way. However, in order to discuss the precision case, so somehow it is quite difficult to discuss the optimization of our estimate for generic situation. We assume that the true parameter is very close to the some point. So true parameter belongs to the neighborhood of some point. So in that case, it is enough to consider this local unbiased condition because usually we consider this is unbiased condition, but we consider that condition, this is average of I, average I equal to this one. But if you take this condition for the Taylor expansion, and we stop this Taylor expansion on the first order, so in that case, it is enough to consider this condition for only one point, and it is enough to consider its derivative condition, this one. So if we take a mean square, unbiased condition for the neighborhood, so then this one converted to the this locally unbiased condition. So it is enough to consider up to the only first order derivative. So first order derivative should be this one. So we assume this condition. And this one is depend on the some point. So at the point, so then we have this point theta. So now we consider this problem. Our estimate theta hat means that the pi hat means that the pair of theta hat and pi. So this assume that satisfy the locally unbiased condition at point theta, then we minimize this quantity. This is gives the somehow fundamental precision limit because state estimation problems can be reduced to the local problem by considering the two-step estimator problem method. So, due to that reason, many people try to discuss that problem. So first, major contribution is, of course, by using the SLD method, but in the case of, yes, SLD, this is done by Hellstrom. So we need to consider DJ. DJ is this partial derivative, and you take Li to satisfy this way, Li. So this is symmetric way. So then Li is called symmetric logarithmic derivative. So Li is symmetric logarithmic derivative. Then we define this quantity. This one becomes the real number, real symmetric matrix. So then we have this quantity J inverse and G and trace. This one gives the lower bound. This is this lower bound comes from a very famous inequality, SLD version of the quantum parameter inequality. So a kind of quantum extension of the parameter inequality. However, this is not so good for the multi-parameter case. So then we need to consider the very complicated one. So recently, this called horrible bound, but horrible bound is very confusing. So because the story is very complicated. So anyway, I explained this one. So firstly, we discuss set of Hermitian matrices in this way, Z1 to ZD, and this one needs to satisfy this one. And we show that for any estimate, there exists. Of course, this one needs to satisfy locally unbiased condition. So for any measurement, estimator pi, there exists sequence G such that this one gives the lower bound. GG is this one. This is Hermitian matrix because this one is not commutative in general. So then this kind of diagonal part is sometimes complex number. But if you extend the I and J, so then that number is it's complex conjugate. So then this matrix becomes the Hermitian matrix. So then Hermitian matrix gives that lower bound. For any locally unbiased measurement pi hat, there exists G such that this one gives the lower bound. And using this inequality, this quantity gives this lower bound. Then it is enough to consider this lower bound. So this is a horrible Nagaoka bound. You need to take minimum of this among the G, but G needs to satisfy this condition. This bound is called horrible bound. Nagaoka called this lower bound. But firstly, derived that this lower bound is Nagaoka, not horrible. At that time, he considered that he employed some very important inequality proved by horrible textbook. So then Nagaoka considered that this kind of lower bound can be easily obtained by horrible one. Then he believed that horrible already proved that lower bound. But I read so many papers written by horrible, but horrible never proved this inequality. So due to that reason, so somehow some people misunderstand horrible bound is a different lower bound because horrible textbook provides another lower bound. So then there is some confusion. Some people consider that different bound is horrible bound. But no, horrible never proved this one. So for example, if you read this horrible textbook, so you cannot find this lower bound. Only Nagaoka's paper can find the lower bound in this way. But maybe it is better to call the horrible Nagaoka bound because this kind of gap from the horrible contribution and this lower bound is not so trivial. Only this is trivial for viewpoint of Professor Nagaoka. So due to that reason, we should call this one is horrible Nagaoka bound. This is very confusing. So now I want to explain this one. So there is any copy of original state rho n, so rho theta, then n copy of this one, and you make a measurement. Then so you have this one. If you consider that strategy, the true bound is given by this one, horrible Nagaoka bound. This is shown by our recent paper, another paper. But sometimes this measurement strategy is very difficult because you need to make some correct measurement across so many copies, not only one, not only two. Maybe you need to across so many n copies. So quite difficult. This is almost impossible to realize that kind of measurement. This is ultimate bound, but not so really practical. So from the practical viewpoint, we need to improve our strategy in this way. So you make one copy measurement this way and this way, POM, but you need to improve the choice of measurement in this way. So adaptive feedback is needed. So in that case, our optimum measurement performance is given as that kind of previous bound. So yes, this bound gives the optimum bound in that kind of adaptive strategy. So thanks to the adaptive strategy, it is enough to consider some local optimization in this way. Later, Nagaoka improve the horrible Nagaoka bound in this way. So in the case of, but he considered only two parameter case. The two parameter case, we have this one. So in the case of horrible Nagaoka bound case, that quantity equal to this one, you need to make absolute value of this trace. In that case, this one is horrible Nagaoka bound. But Nagaoka find that this one can be improved in this way. So we can take absolute value before tracing. So you consider this matrix and firstly take trace, firstly take the absolute value and take trace. So in that case, this lower bound larger than horrible bound because horrible bound take absolute value after the trace. So of course, taking absolute value first is slightly larger than taking absolute value after the trace. Because in the case of trace, there is some negative part on the diagonal part. Diagonal part somehow negative. So then in this case, all of that diagonal part become positive value. So then this one is slightly larger than horrible bound. Later, I expand horrible Nagaoka bound. Expand Nagaoka's bound in the multi-parameter case in this way. But in my paper, at that time, I did not consider that minimization. Slightly, I consider that different problem setting. But essentially, from my previous paper, we can easily obtain this lower bound. That kind of derivation of this lower bound is almost trivial from my previous paper. So then, this one. But here we need to consider B prime. B prime is this one. So we need to consider very big matrix. So each matrix, this is parameter space, and each element is also Hamish matrix in this way. So this is Hamish. In the case of general, this is bounded operator on the self-adjoint. So and also the off-diagonal part should be same. So this one, sorry. This one and this one is the same. So we consider this big matrix. This one consider kind of the matrix on the tensor product system. So tensor product system on the parameter space and the original physical system H. So we consider that big matrix on the tensor product system in this way. So, and we take this one, and pi g is defined. Pi g is defined. I forget the definition, but pi g is somehow only the zij. Pi g is this one. Pi g is we don't take about this trace. Only the ij7 is zj in this way. So ij7 is zj. So this one is the pi g. So this is very big matrix. So we consider this one. So x prime is the element of this one, and we consider matrix inequality for this one, and we take this one. Of course, this minimization is very difficult. So, this one gives us some generalization of the Nagaoka's bound. So, also, this is my master thesis many years ago, 1996, but I get a master degree in 1996. No, 1 year before. But at that time, I write down this one in Japanese. So English version written in the archive version or these proceedings. So in that case, we consider linear programming method, but in this case, we need to consider infinite dimensional linear programming, and its duality problem can be written out in this way. So this is slightly complicated. So we have some matrix S, and this is another matrix A. A is a matrix on the parameter space, and S is a matrix, Hermitian matrix on the physical system. And we need to maximize this one under this condition. And G and X is arbitrary X on the parameter space. And we consider this matrix inequality from the physical system. I drive that. This one gives this bound, this one equal to this one. So this is very my old result. But how to efficiently this one calculate this one? So quite difficult to calculate this one. And we want to unifiedly understand the SLD and Horebo Nagaoka bound, Nagaoka Hayes bound, and this our bound. So is there how to characterize this gap? So this is our motivation. Then our result, so we solve that. We unified the theory for this bound by using a conic programming. So this is very nice, and demonstrate the this way. So we consider this conic programming. So we again we consider this one, but now we consider big matrix, but each component is we add the zeroth element. Previously, my previous paper, this one we B prime consider only the ij, the index run from 1 to d, but we introduce zeroth element. So in this way, we consider this slightly larger system, and X is this element. So then here is the matrix space. B prime is the previous one. This is only 1 to D, but B is larger than this is 0 to D. We consider big system, and we consider someone B. Yes. Separable. So yes. We consider positive semi-definite condition for the this big B. And also, we consider separable cones. So this is the positive semi-definite, and we can consider that system is a tensor product system on the real vector space and matrix space and Hermitian spaces on this one, tensor product here. So this is the step one. So of course, this separable cone is smaller than positive semi-definite cone. So then we can define sequence of this sequence of this one. And B prime is this one. So we consider this one. Previously, B is same. So this one and this one same. So this one is same to B. And in the case of B double prime. So this and this and conjugate each other, slightly different condition. So then we can consider sequence of cones in this way. So SEP and positive cone and this one. So then our final result is the following. So depending on this, we can consider this linear programming on depending on the cone. So yes. So for example, SP1 is this one. This is separable cone and 36 and 37. 36 and 37 is, where is 36? Yes, I remember that. Here is 36. 36 is this condition. For X, we import this condition and this condition. And this one means the corresponding P of M condition. Full measure should be identity. So then we have this condition. And this is the locally unbiased condition. This is 37. Under this condition, we minimize this one for the separable cone. So then this one equal to SP1. This SP1 equal to the original tight bound. So this is the first result. So this is the linear programming first one. And the second one, we can relax this one to the positive semi-definite. So then this one equal to the Nagaoka Hollow bound. This is quite similar. So separable and positive semi-definite. So due to that reason, this one become positive semi-definite. Then this problem can be converted to the SDP. So then you can easily resolve this problem. And in the case of SLD bound is very easy. So we consider P4. We replace replaced by this cone. So then we define P4 in this way by replacing the cone by this one. So then we have this one. And we have another one. So we additionally impose this 48 condition in this way. So then we have another one is P5. So and this one has this one. So we have a subspace of B5. So B double prime, and we have a 48 condition in this way. So then we have a horrible Nagaoka bound in this way. So of course we have some relationship with another cone. This cone with this condition is also we can replace this one here. This is between the P2 and the P4. So then we have a sequence of this one. So this is the largest cone, and this is the smallest cone. So then due to the last order, we have some unified understanding of the existence many cones. And all other cones we can resolve it by SDP, but this one can be, we have to handle this separate cone. So separate cone is very bad cone to solve the linear programming, conic programming. This is almost quite difficult, impossible. So in order to resolve that problem, we need to make some points. So we make some discretization on the some parameter space. So then we have another SDP by discretizing that in this way. So then we have a lower bound in this way. But also we have a gap. We can show that the gap between this separable cone and this smaller problem. This is the SDP. So then the opposite inequality also quite difficult, but we could solve the opposite inequality. So then we have a lower bound, upper bound for this problem. So this part is too complicated. I want to skip due to the time constraint. So maybe almost time. So finally, we have this result, numerical result. So this is done by my co-author. Here is very nice for the numerical calculation. This is P5. We consider the ratio. So this is upper bound, lower bound. This is so upper bound, lower bound is almost same. So but here is not so good. But still, this is P2. This is horrible Nagaoka bound. So we normalize this one. So we make some numerical calculation by using some model. So I want to skip the detail of our model, but this is the number of parameter. number of three case, number of three case, this one and this one must be same. So horrible bound equal to the our type bound number of three. If we have two parameter, we consider two parameter case and we increase dimension in this way. So then we have this numerics. So, but unfortunately, our lower bound is not so good. So until here, we can show that our bound is slightly better than horrible Nagoya bound. So this shown that, not horrible, highest Nagoya bound. This shown that Nagoya bound is not tight in general. So we need to make more complicated calculation even for two parameter case. So, and future, that's all. So thank you very much. So maybe time, I think. Maybe I want to call, ask some question from audience.
Some question or comment? No. I have a short question on your technique. I think the problem is some optimization on separable cone, P1. But,
sorry, who asking? So I'm confusing.
Hey, Mori.
Okay.
A problem is to solve optimization problem on P1, that is separable cone, I think.
Yes, separable cone is very difficult because this is not self-dual cone.
Yeah. So your technique is introduce some approximation of P1, right?
Yes.
Oh, so
by using this discretization. So I make discretization for the parametric space.
Okay, so we can use this technique for general problem on separable cone, right?
No. Because of course, lower bound is always true, even for that's general linear programming. But upper bound, using this one, so our result is composed of two parts. One is inequality. Maybe inequality does not write down. Yes, we have this inequality. Also, using this one, we have a lower bound of this one. This is a discretized one by using the discretization WR. So we also obtain the opposite inequality with some error term. But opposite part, depending on our linear programming form, function form, objective function, depending on objective function and depending on the constraint, we could obtain the lower bound by using this one and some error term delta.
Okay.
So this part is not so easy. So this is depending on our problem, not general.
Okay, I see. Thank you. Any other question or comment? Okay, let's thank speaker again. So all talks of this morning is over. So it's lunch break.